In this video, we're going to look at the last lesson in Chapter 6C, which deals with modeling motion using parametric equations. Now, some things to keep in mind is the difference between projectile, trajectory, and range when dealing with these. So a projectile is the object that is being launched, the trajectory is the path that object takes, and the range, you keep in mind, is the horizontal distance it travels. Some things that we've learned before, back in 6.3, we looked at these two equations. The first one is your horizontal component, and the next one is your vertical component. Now, things to keep in mind is we need to remember that theta is the measure of the angle in standard position. So from the horizontal is what it means. And above all, we did this in 6.3 as well, is remember to sketch pictures. Trust us, it helps when you're dealing with it. So the first few examples they're pretty basic. We're just being asked to sketch a picture and identify what's the horizontal and what's the vertical component on it. So a soccer ball is being kicked. So I have a soccer ball, and it's going to be kicked from the horizontal, and it's being kicked with an initial velocity at 45 feet per second at an angle of 32 degrees with the horizontal. So it's going to be kicked. So here's the foot, it's kicking the soccer ball. It is the path it's going to take. The trajectory is it's going to be kicked at 45 feet per second at 32 degrees with the horizontal. So right here is your 32 degrees. And we're going to label the force. Let's label it on top of the trajectory that this is 45 feet per second. So really that's what we're looking at for it. And so if we want to find the horizontal component, we're going to use the equation x equals our force times the cosine of theta. So x equals 45 times the cosine of 32 degrees. If we put that in our calculators, we would get 38.2, and that's labeled feet per second. And we do the same thing, but this time we're going to do it with our vertical component. That's y equals f sine of theta. So y equals 45 sine of 32 degrees. And that would be 23.8 feet per second. Now, when you're dealing with story problems like this, you're doing these application modeling problems, keep in mind it must make sense contextually. I mean, if you're kicking a soccer ball, the soccer ball is going to go further horizontally than it is going to go vertically on it. So when you're looking at your answers, and part of the reason why you draw pictures to get your mind right with, well, if I'm kicking a soccer ball, I'm trying to kick it further horizontally than I am vertically for it. The next one, you have a stream of water is shot from a sprinkler head with an initial velocity of 7.5 meters per second at an angle of 20 degrees with the ground. So we'll do the same thing. Here is the ground. Here is the sprinkler head. And it is shooting out water at an angle of 20 degrees with the ground at 7.5 meters per second. And this is 20 degrees. So when we do this one, let me change the color to match it up to the previous one, purple. And we're dealing with, and I'll stick with blue, the horizontal. X equals f cosine of theta. I would have x equals 7.5 meters per second times the cosine of 20 degrees. Again, type that in your calculator. That is about 7.0 feet per second. And we do the same thing for the vertical. Y equals f sine of theta. So y equals, again, the 7.5 meters per second sine of 20 degrees with the horizontal, and that is about 2.6 feet per second. My apologies, that is meters per second for both of those. And again, contextually with this problem, if you have a sprinkler on the ground and it's shooting water, it's going to shoot further horizontally than it is vertically in this case. But in this one, we have a rocket that is being launched with an initial velocity of 17 feet per second and an angle of 85 degrees with the ground. So I'm not even going to bother to draw a rocket, but I do know here is my ground, and the rocket is being shot off at an angle of 85 degrees with the ground at 17 feet per second as the initial velocity. Setup is going to be the exact same. X equals our force, 17 feet per second times the cosine of our angle. And the horizontal is really the same thing, except for it's going to be sine on it. Go to the calculator for both. I get about 1.5 feet per second for the horizontal, and I get about 16.9 feet per second for the vertical. And again, this makes sense. If a rocket is being shot up, it's going to try and go higher than it is going to go horizontal for it. So this is just the main idea for 1, 2, 3 is get used to drawing pictures, get used to what is a horizontal component of velocity and what's a vertical component of velocity. Very similar to how we've dealt with forces before, but the front page deals with horizontal and vertical components of velocity. Now what the back page looks at is the back page looks at the parametric equations for the path of a projectile. And all parametric equations come in pairs, one for x in terms of t and one in y in terms of t. So we deal with x equals t times v, that initial velocity cosine of theta. And this is our initial velocity. How fast is it usually initially going, at what angle to the ground, and for how long is it going there? And that's telling you the path horizontally. For the y, notice it's the same idea in the beginning. There's a t, there's initial velocity on it, but this time there is a sine because we're dealing with vertical. Now we're looking at also subtraction. On this case, 1/2 minus gt squared. G is your gravity. Now to keep in mind for gravity, if we're dealing with the metric system, we have 9.8 meters per second. Or with our system, we look at approximately 32 feet per second. And we also have to keep in mind something that is easily forgotten is that there is usually an initial height that an object is shot from. And so that's what h sub 0 is. So these are the two equations that we use for modeling the path of a projectile with parametric equations. So our job is really to kind of identify what are these variables. Now keep in mind, gravity is going to be consistent. You just need to know which one do you use. Do you use the 9.8 meters, or are you dealing with feet and you're going to use 32? The initial height is going to be given to us in the problem. We have to read it and make sure we kind of underline information that we're given. And the same, the initial velocity for both the vertical and the horizontal, those will be given to us in the time. So really, I guess that means we need to focus on how we read the problems and identifying the information that's given to us when we read them. So Casey Clark led the Women's Pro Softball League in strikeouts in 1998. Suppose she throws the ball at an angle of 5.2 degrees, so that's important information. She throws the ball at 5.2 degrees with the horizontal on it. That sounds like theta to me. At a speed of 67 miles per hour, That sounds like initial velocity to me. Write a parametric equation that models the path of the softball. Remember to convert 67 miles per hour to about 98.3 feet per second, same unit as gravity. Now, this problem, just so you are aware, it is telling you 67 miles per hour is 98.3 feet per second. We need to make sure we have the same units for gravity on it. The way that number, I know it was given to you, but to find it, you take 67 miles in 1 hour, and we want to change to feet per second. So the first thing I'm going to do is I'm going to change miles to feet. So there's 5,280 feet in 1 mile. The miles cancel. Boom, boom. So now I have feet per an hour. But I want per second. So I know 1 hour is 60 minutes. And I know 1 minute is 60 seconds. So now the hours cancel, the minutes cancel, and I get my feet per second remaining on this. So I would take 67 times 5,280, and then it looks like I would divide by the product of 60 times 60 on it, and that does give you 98.3 feet per second. It was given us the problem, but it's nice to be aware of how to do the conversion on it. So we're looking at the first part. Write the parametric equations that model the path. And there's two parametric equations. There's one for x and there's one for y. So x equals t times the initial velocity and then cosine of the angle. Well, this was all given to us on it. We're going to write the equation. We know our initial velocity. We know it is 98.3 feet per second. And we know our height, our angle of 5.2 degrees. So we have 98.3 cosine of 5.2. And I'm going to put the variable t in between the coefficient and the cosine. Makes it easier to type in, especially with your calculator when you're looking at it that way. Don't put it at the end here, because when you type it in, it's going to look completely different than the way it's supposed to. So insert your variable between the 98.3 and the cosine of 5.2. Now the next equation is a lot longer. It's the y, but it's the same beginning, t times initial velocity, but this time sine of theta. But we have to realize gravity plays a role. It's going to take away from the height, so minus 1/2 g t squared plus, well, we need to know where we started from, our initial height. Again, the information is given to me. I just need to plug in what I know and simplify. T is the variable that we're trying to just use. We're trying to estimate the time, the position that it's at for each time. So I have the initial velocity of 98.3 sine of 5.2 degrees minus 1/2. Now we are in feet per second, so I'm going to use 32 t squared. And the initial height, it was not known to us yet. We'll find it out later, so I'm just going to put the plus h of 0 there and just leave it there for a moment. Now the simplifying, when I'm simplifying, I'm going to notice I have a squared and I have a plain old t, so it looks like a quadratic to me. So when I simplify, I'm going to write it a little bit out of order. I'm going to do this part first. Minus 1/2 times 32, so that's negative 16 t squared. And then I'm going to put the linear term next. Plus, again, 98.3, split the 98.3 into sine with your t. Sine of 5.2 degrees. We do not know our initial height yet. Most of the time that will be given to you is just in this part A prompt, it's not. These, as of right now, are the two parametric equations that we're dealing with for it. We'll use them to solve the next part. It says the distance from the pitcher's mound to home plate is 43 feet. If Casey releases the ball 2.7 feet above the ground, how far above the ground is the ball when it crosses home plate? Now we're dealing with this. Kind of think about, there are two equations you're trying to figure out. You want to deal with the x and you want to deal with the y. Now, in my opinion, the x parametric equation is a lot easier to deal with. There's less writing. It's pretty straightforward. All you're going to deal with is you're going to plug in and solve for the time. So we know, based off what's given to us, the distance from the pitcher's mound to home plate is 43 feet. That is our horizontal distance. That is our x value on it. So I know 43 equals 98.3 t cosine of 5.2 degrees. Now if I want to solve for t, I'm going to take 43 and I'm going to divide by the 98.3 and the cosine of 5.2 degrees. And that's going to give me my value for t. Don't just watch me write it down. I would practice it in your calculators. This is the biggest issue that we have, is you're not typing them in properly with the calculators. Is when you hit the division sign with your calculator, either use the fraction feature by hitting the alpha y equals button on the calculator, or put this in a parentheses. You have to choose one of those two options, because the time it takes, if I type it in properly, is about 0.44 seconds. Always start with the x in this case first, because it's the easiest one to find. And that's going to give us our t value, and that's what we're looking for. So the easiest parametric equation is the x. So always start there. Now we're going to take that value, because it was so easy to plug in to x and find the information given to us. We're going to use this to answer the real question: how far above the ground? So that means I'm going to use my equation that y equals negative 16t squared plus 98.3t sine of 5.2 degrees plus my initial height. Well, from this prompt, we were told our initial height is 2.7 feet. So I can plug that in, but also realize negative 16t squared, I know what t is now. It's 0.44. 98.3t, well, that's 0.44 sine of 5.2 degrees plus my initial height, which is 2.7. So we start with the easiest parametric equation, the x1, because that allows us to find t, saying it enough, really easily. And then we can use that t in our y parametric equation. Now for this, you're going to go straight into the calculator. Don't find each individual part. What I do want to know is I want to see that written down for it. And when I do that, I get about y equals 3.5 feet. So to answer the question, how far above the ground is the ball when it crosses home plate? The ball is about 3.5 feet above home plate. So when you're dealing with the two parametric equations, make sure that you choose the easiest one to solve for t, which is the x, and then use that to find your y. Last problem is, one of the earliest pitchers in the history of professional baseball to throw a perfect game was Addie Joss of the Cleveland Naps in 1908. Suppose that he throws a ball at an angle of 5.1 degrees. So let's kind of keep this in mind. Angle of 5.1 degrees, that looks like my theta. At a speed of 85 miles per hour, that looks like it could be my initial velocity. The distance of the pitcher's mound to home plate is 60.5 feet. That looks like, distance from pitcher's mound to home plate, that looks like it's an x value. We'll come back to that. If he releases the ball 2.9 feet above the ground, well, that looks like an initial height. How far above the ground is the ball when it crosses home plate? Seems more complicated than the other problems, so so much information is given to us. What do we know? Well, first off, I know theta. That was given to me. Theta is 5.1 degrees. I know my initial velocity. That was given to me as 85 miles per an hour. I also, in the blue, the distance from the pitcher's mound to home plate, that's a horizontal distance. So x is 60.5 feet. And the last piece of information given to me is my initial height. The ball was released 2.9 feet from the ground. Well, that's really everything. If I look at my parametric equations up above, I got a x, I got a cosine of theta, I got initial velocity, I have a sine of theta, I can do initial velocity, gravity makes sense, but wait a minute, gravity is feet per second, my initial velocity is miles per hour, I'm going to need to fix that, and initial height there. So really, I have everything I need. But the hardest part, and I'm going to start with this first, because initial velocity is in miles per hour, but gravity is not. And we must match gravity for it. So I'm going to take 85 miles per an hour, and I am going to change it again to feet per second. Remember, we want to get rid of miles, so I'm going to put miles on the bottom, and I have 5,280 feet on top. Now, that means the miles goes away, they cancel out. I'm now feet per an hour, but I don't want feet per an hour. I want feet per second. So 1 hour is 60 minutes. I don't want minutes, but the hours do cancel. So hours gone, hours gone. I'm now in feet per minute. I want to change that into feet per second. So 1 minute is 60 seconds. The minutes cancel. I'm now in feet per second. So really, I'm going to do 85 times 5,280 and then divide that by the product of 60 times 60, which is about 124.7 feet per second. And that is my new initial velocity. The main idea is your velocities have to match on it. You're either in meters per second or you're in feet per second. They have to match gravity in order to keep with like terms in the equation. That was really the hardest part, is converting from miles per an hour into feet per second, because the rest is all can you plug in to an equation. And so I have x equals t times my initial velocity cosine of theta. Well, if I take a look, x equals t, and I don't know, but I know my initial velocity, 85. Wait, we changed that. We changed that into feet per second, so 124.7 t cosine of 5.1 degrees theta. Remember, we know what x is now. I know that x is 60.5. So 60.5 equals 124.7 t cosine of 5.1. And to solve, I'm going to take 60.5 and I'm going to divide by 124.7 cosine of 5.1 degrees. Again, make sure you type it in your calculator right. Either use the fraction feature, which is the green button, alpha y equals, or put this in a parentheses if you're typing it in one line. And that is going to give you about 4.9 seconds. That's how much time it takes to get to home plate, the horizontal distance. So notice, and I had to erase and fix the problem I made, is I did change my initial velocity. It was no longer 85 miles per hour. We changed it to 124.7 feet per second, so I needed to make sure I corrected that. The parametric equation is the x equals 124.7 t cosine of 5.1. And we plug in what we know, which was the horizontal distance. That allows us to find t. And just like before, we can use that in our y equation for it. Y equals t times initial velocity sine of theta minus 1/2 gt squared plus my initial height. We know everything. I'm going to write the parametric equation first, though. I know my initial velocity is 124.7. So 124.7 t sine of 5.1 degrees. We're in feet per second, so that'd be, gravity would be 32 then. T squared minus 1/2 32 t squared plus the initial height. Looks like it was 2.9. And I'm going to just write the parametric equation in the order that we have. The negative 1/2 32 t squared becomes negative 16 t squared plus 124.7 t sine of 5.1 degrees plus 2.9. So highlight them in orange. These are the two parametric equations. You can type them in your calculator. You can actually see the path of the projectile. But what I want to know is what's the height after, 0.49. I'm just going to stop.